Hey guys, welcome to yet another video on light. Okay, quick recap. So far we've done a reflection and refraction. Main difference, reflection stays in the same medium, gets bounced off, whereas refraction travels through the medium, right? So for reflection, the only thing we know is that the main law is that angle of incidence is always equal to the angle of reflection. And the angles are always, in all cases in light, always measured with respect to this normal, right? So for refraction, what is it all about? Refraction, we introduced you to a new term called the optical density, okay, also known as the refractive index. It is known by the formula sine of I equals sine of R. Remember, this is Snell's law, and we actually define this to be refractive index. Okay, so with these two in mind, we're gonna go straight into the video of total internal reflection. What's this all about? Okay, so without further ado, we'll just go straight into. All right. Okay. Before I start the demo, this is a very good demo that I found off the internet. You can see a glass prism is being used here. A ray of light actually shines from air into the glass prism and then out through into the air again. Okay, as you can see over here, there's no bending of light because the angle of incidence is always zero. You can see it's always, every time I were to draw a normal here, which is always perpendicular to the glass surface. As long as it passes through the center, there will not be any bending here, okay? So the only bending will occur when it exits the glass block. Okay, so just to show you a bit of a demonstration of what this means and just observe the behavior of the refraction, okay? So let's go. So as I increase the angle of incidence, you can see my angle of reflection also increase until boom reaches a particular point whereby what happens? Oh, no more refracted ray, only reflected ray. Okay, so one more time just to show you, you can see as my angle of incidence increase. Okay, at the same time, you can see my refracted ray also gets a little bit dimmer, and this one actually starts getting a little bit brighter. There's actually a very light reflected ray, right? Okay, just let it go on a little bit more and boom. Okay, this exact moment whereby all the rays become a reflected ray, where this reflected ray becomes very bright, and you can't really see it here, but there's actually a refracted ray that goes along the surface. So this is known as a very critical point in your life. Oh, okay, let me rephrase that. This is known as a critical point, okay? And this is known as a critical angle. Okay, what's a critical angle? Critical angle is basically the angle whereby you, the angle of incidence in the more dense medium gives angle of refraction of 90 degrees. Okay, why is that critical? Because after this critical angle, whatever this may be over here, I read it to be about 42 degrees. After 42 degrees, see what happens? You can see it becomes total internal reflection. I only have reflected rays. Okay, so just to go back to this, okay, if I were to just make a quick animation, okay, as long as I increase the angle of incidence, see what happens? I actually have a weak reflected ray versus a refracted ray, right? So refracted ray, you can see it actually bends away from the normal. Why does it bend away? Because imagine the truck here. As the truck goes in, the left tire touches the surface first. So the left tire, since it's entering air, it will go a bit faster. So vroom, it will basically drift and move away from the normal. So this is pretty straightforward, but once it goes some more, oh, there will be an angle whereby this refracted ray will be increased until it's just along the surface. That means the angle of refraction is 90 degrees. And I mentioned to you, this is a very critical point. This is known as your critical angle. Okay, why is it critical? Because anything after this, I only have total internal reflection. Okay, okay, so that's it for basically total internal reflection. Okay, or just to recap everything, you can see if I show you all the screenshots in one shot, initially it's like that. There's no refraction. If I increase the incident ray, the angle incidence have got a bit of refraction, bending away from normal, goes to a special angle here whereby the angle refraction is 90, so this is known as critical angle. You get also a reflected ray, and anything bigger than the angle, critical angle, the incidence bigger than the critical angle, you get TIR, total internal reflection. Okay, so just a quick recap. Critical angle is basically the angle of incidence in the optically denser medium when angle of refraction is 90 degrees. Okay, and there are two conditions for total internal reflection. Okay, first one, very important, your light ray must travel from a denser to a less dense medium. Because if it is from a less dense to denser medium, you will never have total internal reflection, whatever your angle. Okay, let me just show you based on this very quick and simple simulation. You can see here, if let's say I have something that is moving from less dense into denser. So this one is uh, a refractive index 1, this is refractive index 2.5. You can see as I increase my angle of incidence, I will always have a refracted ray. So you see, I will never have any in any reflection, total internal reflection. But if I were to shift it the other way around, oh, let's check this out. Look at this. Look at this. As long as you can see my angle of refraction is bigger than my angle of incidence, right? So there will come a time whereby my refracted ray will reach the surface first before my incident ray can reach the surface. So you see, and 3, 2, 1, boom! You see, once it reaches that surface, everything gets converted to total internal reflection. Okay, so this is the reason why it has to travel from a denser to a less dense medium. Okay, and of course, the second condition for total internal reflection will basically be just that the angle of incidence is greater than your critical angle. All right, that's it. Hope you enjoyed this video. Okay, I'll see you guys in the next.